Okay, good evening, and thank you very much to everyone for coming this evening. I'm Peter Wilson. I'm an engineering director with Google here in Kirkland, and it's my pleasure tonight to introduce Shiva, who's going to be talking this evening. Before we do, I have some announcements I've been asked to make. Firstly, the restrooms are in the hall outside. Secondly, we're going to be videotaping this and putting it up on Google Video, which is one of several great products written here in Kirkland. So this will be on Google Video, just the presenters, not the audience. So if you don't want your employers to know that you're here at Google tonight, you don't need to worry about that. We encourage you to hang around after the presentation's over and continue the discussion, and myself and Shiva and a bunch of the other engineers from Google will be here. And then lastly, we have 3 future events coming up. On June 7th, Jen Fitzpatrick is talking about user experience at Google. On June 21st, Alan Spurdas is talking about a study of ORCUT. And on June 28th, we're talking about security at Google. So I'd encourage you both to register for these, and also please forward the invites that you got for this event to any friends or co-workers you think might be interested in attending any of those events. So that's it for the announcement. The talk tonight, Building Large Systems at Google, it goes without saying really that Google deals with huge amounts of data and a huge number of users. And so Shiva's going to talk tonight about basically how this all works and how we do what we do and how we make it scale. Shiva is an engineering director and a Google Distinguished Entrepreneur here at Kirkland. Google founded this office here and has been my fellow director in the year that I've been here. He's been responsible for many of Google's advertising products and the Google Search appliance. Prior to working at Google, he co-founded Gigabeat, a startup which was purchased by Napster. He has a bachelor's from UCLA and a PhD in computer science from Stanford. So please join me in welcoming Shiva.
Right, thanks, Peter. So before I get started, I want a quick show of hands. How many of you have seen a talk by a Google engineer in the last 9 months? Okay, that's great. That's not too many. Because we do tend to reuse some slides. So we don't spend too much time on certain slides. So I'm going to talk about building large systems at Google. So it's really 3 different components. We have a bunch of Google products that you've seen. It's in search, in advertising, in building email, building talk, and a whole bunch of other things. And typically all these products, they tend to be on top of a very large stack of distributed systems and some infrastructure that we have built up over time. At the bottom of the stack, we have a computing platform, which is a whole bunch of machines in a bunch of different data centers, which have been designed and built up over time to work with all these different products. I'll be talking more about these things. And by the way, if you have any questions, just stop and interrupt me, because I know what my slides say, and I'll get really bored if I just talk to my slides. So just stop, interrupt me, I'll be happy to talk more. The mission that Google has had for the last 7 years is to organize the world's information and make it universally accessible as well as to make it useful. One question that people typically ask is how much information is there? The answer is a lot. So if you just look at just the web and how it's been growing over the last few years, I remember when I started Google about 5 years back, we had close to maybe 1 billion documents. And over the last years, it's going to be a lot larger than that. And if you just take away the web, there's even a lot more than that in terms of your personal email, your files, and databases, and we've been expanding into other areas too, in terms of video, in terms of radio, print, etc. as well. So in terms of products, you've seen a bunch of these things. Initially, we started a few years back with the web. And our charter was to say, let's not do anything but the web, right? So that was the initial charter, and then over time we kept expanding into more and more media formats in terms of images, video, and into enterprises, into scholarly publication, maps, and recently into areas like chat and voice over IP as well. So this is a list of all the Google products that have been built up over time. If you just look at the list of products we've launched from this office right here in the last year and a half, it's quite a bit. So there's a mix of products in a bunch of different areas. There's a lot of work going on in search, in crawling, and indexing. So one of the products we've launched in the last year is Google Sitemaps, which is a mechanism through which webmasters tell us what they have on their site, as well as get information from us as to what we believe we know about their site. Then there's a bunch of client software. For example, there's Google Gadgets that launched about a couple of weeks back, and this is part of Google Desktop Search. Google Pack is another one that launched about 3 months back. There's a lot of work going on here in terms of Google Maps. For example, a lot of the rendering for the geographical information of maps, as well as for specific countries, is happening out of here. Google Video, the client and most of the front end was built out of here, and we're expanding into more of those areas. Talk, Google Chat, and a variety of the other things have been primarily built from this office in just the past year and a half. So every one of these products that we have is hard because there are more and more users using these different pieces of applications. And every one of them has more data, and every one requires more results, better results with time. So for example, if you pick any of our products, we want to make sure that by analyzing what users are doing, we want to be able to give them better results over time. So every single one of these products keeps expanding in terms of the amount of data we process, as well as the number of users who actually want to use this area. So the overall goal that we have for systems infrastructure, that is the pieces of software or the stack that is necessary to support all these different products, is that every few months, every day, we want to keep building out larger scale as well as higher performance infrastructure to support these applications, because everything is growing. And also, we want to make sure that we don't go bankrupt. So we focus on making sure that the price per performance is getting better over time, and the ease of use as well. We do not want to have every single application build out entire parts of the stack. So we want to make sure the infrastructure that we build is scaling as well as supporting more users, and is easy for the folks within the company to deploy more and more products with time. So any questions so far before I get into the depths of systems infrastructure? Okay. So I'm going to talk about 3 different parts over here. So just a reminder of this. So Google products, and then we have the system infrastructure. I'm going to talk about the hardware computing platform later. But in terms of the infrastructure that we have, I'm going to talk about Google File System, which is a mechanism. It's really a large distributed file system into which we throw in lots and lots of data. And then we have a couple of computational models as well as storage models that we'll be talking about as well. So GFS is yet another distributed file system that we built up in the last few years. So the question is, why do we want to build another file system as opposed to reusing some existing file systems? As it turns out, we have a lot of flexibility in what we do. We control our applications, we control our operating system, as well as the machines on which we run these things. So based on this observation, we looked at a whole class of applications and realized that certain of these things have a large amount of read-write bandwidth, as well as we need to have reliability over many, many machines. And we want to make sure that it works across multiple data centers. And also, the actual units of files are actually pretty large in size as well. So we need to have a bunch of applications that can store huge amounts of data across lots of machines, as well as in multiple data centers as well. So that's the reason why we started building Google File System. So the way in which it kind of works is, there's a GFS master, and the master is what every single application talks to. And the master controls a whole bunch of these chunk servers. So chunk servers are essentially, you can think of them as machines which have certain fractions of content that is localized to that particular machine. And what the master does is, it takes any file that you want to store. Let's say you want to store a terabyte of information. It takes a file and breaks it up into chunks of data and says that you, machine number 55, you will be responsible for storing this particular set of chunks. And the other component of the master is to make sure that it's replicated across multiple machines. So if a machine goes down, and we know the machines will go down, then at least the application can survive by talking to another bunch of machines very easily. So the master essentially manages the chunk to location mapping and make sure that the underlying systems are scaling in terms of load balancing as well as redirecting traffic to the machines that are least loaded. And also when a machine goes down, then the other chunk servers sort of react to that by transferring data automatically between the peers themselves. So in terms of the GFS usage at Google, we have a lot of these GFS servers, and we have all of these clusters, and they scale to very large amounts of data. So typically, the clusters have 1,000 machines or a few thousand machines, and the number of clients that talk to the master are pretty large as well, and are growing with time as well. And you can be pretty impressed with the amount of read-write bandwidth that goes through these systems. And every one of these things is part of our say the ads pipeline or the search pipeline or any other product that we talked about in terms of being the core storage on which we store all our data.
Question?
Yeah.
Is there one master per cluster?
So the question is there one master per cluster? So it depends. So in a bunch of cases, you want to make sure that there are a bunch of multiple masters, so that if a master actually goes down, you could reliably hand it off to another master as well. But you want to make sure that that there are multiple masters that are really mastered at the same time, right? Because you don't want to have them controlling which chunks are going to which machine and making different kinds of decisions. So you can imagine there being a leader election that decides which, out of all these thousands of machines, which ones do I want to become the master, but then there will be a master handoff process as well. Some of these things can be automated, some of these things are more manual as well. So for example, if a machine goes down, it could be that you may have to restart a bunch of master machines so that they do take over some of these, the actual task. But you also want to make sure that when a machine goes down, there's enough persistent storage so that when another master comes along and picks it up, it would have complete state and can do useful things with that data.
But are there multiple instances of GFS?
Are there multiple instances of GFS? Yes, there are lots of GFS cells, and different applications could run different GFS cells. And there is actually a lot of work where there are standard GFS locations where people actually can store data into as well. So depending on the application, you can either choose to use an existing GFS cluster or make up your own GFS cluster as well.
Yeah, are the masters self-managing, or you have another master which manages the master or something?
So the question is, are the masters self-managing? The answer is, you would like them to be, right? And in the cases they're not, because there could be bugs or because something hasn't been built up, you want to make sure that you have enough reliability in terms of moving a master from one set of machines to another set of machines.
So is the leader election algorithm more of a bully algorithm, or?
So the question is, what is the leader election algorithm? And the answer is I don't know the answer to that question. But there are lots of different options, and there are issues around whether you want to have leader election in the context of one data center or multiple data centers, and depending on how much network partition you expect to happen, you may choose one versus the other. And also, you got to look at how often do machines go down, and how often do the masters actually go down. Because arguably, you could actually say that the master could be in a much more reliable machine than other machines. I mean, these are options that are made on a pretty daily basis.
But in theory, any machine in the cluster could become a master, or only selected machines are eligible?
So the question was, can any machine become a master? Again, it depends on the application. There are certain classes of machines which are slightly more reliable. So it depends on again, the precise context. You may be willing to lose some data in some cases, again, depending on how much money you want to spend versus how much reliability you want. That's why looking at the price per performance number on a per application basis is very important. For example, we don't want to lose any logs data. right? In that case, you may be willing to invest in a lot more money to have much better master election algorithms or much better machines in those different situations. On the other hand, if it's my personal GFS cluster, maybe I don't care as much. But again, the application can make its own trade-offs. But you want to have enough libraries, functionalities, and building blocks so that when an application chooses to do one versus the other, they have enough flexibility. Okay?
What's the maximum range of chunk servers per master pool?
What is the maximum range of chunk servers per master pool? The answer is I don't know. So it depends again, right? So you can actually look at the number of. So let's say that if a typical chunk size is around 64 megabytes, that's a suggested number. But you could arguably have chunk servers that process chunks that are larger than that. So maybe the question to answer is how much is the storage of? I mean, I think a more interesting question to ask is what is the storage of? Given 1,000 machines, how much can you store, how much reliability can you get, and how much read and write throughput can you get? And that depends again on how you want to configure it. There will be some default configuration, but these are things that you can elect to change as well. Does that kind of make sense? Yeah, and again, the key is to make sure that we have enough infrastructure so that people can make different choices, and there's enough flexibility, and we just have to have the right building blocks along the way so people can choose the right numbers. So I'm going to move from GFS to a couple of other systems on top of GFS. So GFS has been around for a while, and it's a very reliable store, and there's anecdotes that we've lost less than 64 kilobytes or 64 megabytes of data ever since GFS was deployed. So now that that's a reliable storage mechanism, we want to start processing data and doing interesting things with it. So one of the example applications which runs on top of GFS and processes huge amounts of data and does interesting things with it is MapReduce. I'll be talking about BigTable as well. BigTable is more of a lookup service rather than a log structured, let me store all my data kind of model. I'll get to that in a couple slides. So MapReduce is a way by which you can have a lot of very complicated aggregation kinds of computation happening on large amounts of data. So imagine that we have a whole bunch of web pages. And what we would like to do is we would like to count up the number of words that occur across all the different web pages. So what the map phase would do is it would try to take all the records. So in this case, it'll be the pages will be, imagine them to be stored on GFS. So what you could do is you can take every single page, stream it through MapReduce, and the mapping phase would essentially yield key value pairs of the form word to the URL of the page. So it essentially translates or maps from one view of the data to another view of the data based on what you would like to aggregate with. So in this example, the mapping phase would take all the web pages and would create a key value pair of key being the word and the value being the URL of the page. Reduction, what it does is it takes a whole bunch of records which are of the same key type and then try to aggregate them by doing a bunch of things and producing the final output. So everyone who uses this model of MapReduce would write essentially two phases. Everyone, as in people in the company who want to process a large amount of data, say a terabyte of data on 1,000 machines, would take the data and would make the mapping steps and the reduction steps and would run this on a large number of machines. And the underlying library, which is the MapReduce library, would take care of the messy details. For example, how do you move data from one machine to another? How do you make sure that when a machine actually dies, that it will automatically recover and the intermediate results are not being lost? So that's really what MapReduce does. So here's a pictorial view of that. So again, you'd see that the central component over here is GFS. So GFS that's over there has lots and lots of data. And all the boxes in there are the chunk servers. So every one of the chunk servers has, say, a bunch of a partition of the file that it would like to be map reduced over. That is, you want to have the application decide what to analyze over the data. So what the application would do is it will take all this data and then applying the mapping step will produce a whole bunch of these key and value tuples. And then we have a shuffling step which essentially aggregates all values of the same key type. So over here we have that all the K1s, which are different machines, which are all getting their data from GFS, will all be shuffled and will be sent across to the reduction step, which will likely be on another machine. And then the reduction step would go and aggregate all the values within that key type. And finally, after that reduction step is done, which could be, for example, a sum or a filter or whatever you want to do, then it will be returned back into GFS for additional processing. So that's the high-level overview of how map reduction works. Any questions about it so far? Okay. So why do people use map reductions? One is it actually works across a whole bunch of machines. It's an interesting computational model. It's a nice way to partition any given task into a whole bunch of these map and reduction steps that can be sent across lots of machines. Machines can die, and the system will just recover automatically. And it's scalable. You can just keep adding more and more machines. And also, it's a nice computational model in that it works across a whole bunch of different applications. It works across search, it works across ads, it works across video. Any product that you can think of has at some component, has at some point in its evolution a whole bunch of map reductions or analysis that is going on to make sure that we understand what the users are doing, or to pre-compute a bunch of data that will be useful back to the end user. Okay, I'm going to switch to BigTables. Any questions about GFS or map reduction so far?
Could you give a few more examples of using MapReduce to solve particular problems? Presumably, you find that you can turn a whole bunch of things into MapReduce that you wouldn't have thought you could.
Right. So the question was, can I give a few more examples of map reductions? There are a bunch of applications. One of the simplest ones is, say, a grep. So what you would like to do is, let's say you want to run a Unix-style grep, where you want to take a whole bunch of data, and then you want to do a word count over that. So imagine a file, imagine a whole bunch of files, and you want to do a grep to compute a whole bunch of keys that are interesting to you, and then do a word count on top of that. So what you would do in that case is you would make each of the files as files in GFS. And then the mapping step will take the files and will map it into, say, for example, line numbers. And then the counting step would actually be done in the reduction step. Or another example would be sorting. Right? So take something as simple as sorting and say that I want to sort a terabyte of data. So what I would like to do is I want to aggregate essentially all the records with the same key into the same machine, and let me do some sort of aggregation on top of that. Again, that will be a natural thing for map reduction. At a higher, at a sort of more product-specific level, we could think of if I have to think of an example in the crawling pipeline or indexing pipeline. There are a bunch of maybe 20 different map reductions that run along in every single part of this pipeline that do various different things. Again, it's a matter of looking at data with a whole bunch of records, and again, aggregating the keys and maybe counting it up, filtering it out, and then you write it back to GFS. Then you have a second map reduction that will come along that will again work on top of this data and then go along in every step of the pipeline. I'm not sure I was very helpful with that. Yeah.
So MapReduce technologies you described, it sounds like an interesting way to distribute computation. The question I have is, have you found any problems that MapReduce was not enough, that you needed some different way of distributing computation?
So the question is map reduction enough? Map reduction solves a large class of problems very nicely, but there are a bunch of cases where it doesn't do the right things. So what we do is we, every few months, we have a new set of problems that come along, and people go and work on building new computational models on top of GFS, and it doesn't have to be in our productions. So we haven't talked about a bunch of things that we've done in-house that are in our productions. But it's a nice convenient tool to do a bunch of things very easily, especially if you've done any simple things like counting or filtering, and you have too much that doesn't fit into memory, then you would want to use MapReductions. But there are other things where you don't actually do filtering and counting or thresholding, in which cases you would want to do something else. But this does not attempt to be the ultimate parallel programming language, because that is different as well. But it works well across thousands of machines for certain kinds of tasks. So we talked about GFS, which is our file store. It's a log-structured file system we talked about. We can store whatever we want to store into that. MapReduction is a computation on top of GFS. So another thing that we have that works on top of GFS is BigTable. So BigTable is you can think of it as a lookup mechanism. So we have a lot of structured and semi-structured data at Google, and what we would like to do is we want to go and quickly query what are different attributes or what are different values that correspond to a given key pretty fast, as opposed to, say, streaming through GFS files and doing a grep on top of that. So it's a lookup table, and traditionally people have thought of databases that front. So the problem that we have is that the scale is very large. We have lots of URLs and lots of blob data. For example, let's look at Maps, which is something we launched about a year back, and that has so much of data, and you don't want to you want to have a storage mechanism that you can go and quickly look up, given a key, what the value of that particular row would be. And the problem is that you can't just throw it into pick your favorite commercial database, because the scale doesn't quite work. It's way too much. We have tried in the past few years to use commercial solutions, but they haven't worked, partly because they are too expensive, or they don't have enough reliability, or they don't work across 1,000 machines, and pick your insert your favorite set of problems. And also the other key is that by controlling the low-level storage, you can do a bunch of optimizations so that you can control how fast something would work with a certain kind of computation. So that's why we started building BigTable about some few months, year back. And also it's just fun to build large systems, so we do that. So the key features is that it's a map, as I just said. Given a key, you want to get back a value, as opposed to GFS, which is where you store all your data. So imagine how do you build a distributed hash map or a distributed gist map. And you want to scale to thousands of machines, and you want it to be fast, so you want it to be as much of it in memory as possible. And also it has to support lots of reads and lots of writes. And also support efficient scan. So these are all the kinds of problems that BigTable solves. And also, it's reliable. You can take out a bunch of machines, you can add in a whole bunch of machines, and the whole system just magically works by doing load balancing, by moving data around, by just reconfiguring itself, so that you can just keep adding more and more machines while the system is serving, and it doesn't lose data, which is very important. So in terms of building, yes?
The previous page, it said it was a mapping key to value. Is it also sorted by key?
The question is it also sorted by key? It's actually surprisingly an implementation detail. As it turns out right now, there is a bunch of sorting that's going on at the key level. So scanning is pretty efficient. So if you want to give a range that says, I want to get back all the tuples within this, within one range to another, then it would support that. But they haven't sort of said that that's going to be true a year from now in terms of the API. But I suspect it will be, because scans are pretty important to do as well. So, yes?
Can you talk a little bit about to what extent did GFS and BigTable wind up doing the same thing? For example, coping with machine failures? Or does BigTable rely on GFS for everything like that it needs?
So the question is, how do BigTable and GFS compare in terms of machine failures? So GFS is a storage model, and this actually is a nice segue into my next slide. It talks about building blocks. And one of the things that BigTable does use is GFS. So all the storage happens on GFS, and there's an abstraction on top of that. And there are other components that are very relevant as well. Like there's a distributed log service that works across multiple machines, and there's a scheduler that makes sure that machines can go pretty well. But I think GFS is very reliable on its own. BigTable, what it does really well is it's a nice way into which you can store data, modify data, and keep growing the repository and do lookups, which is not something that GFS actually supports. So these are two different layers.
But I think you may have answered my question. Can I ask you to compare the API from a programmer's view to GFS versus BigTable? What sorts of operations are present in BigTable that aren't in GFS?
Yeah, GFS is very low level, right? So you want to store a bunch of data into it, and what it supports is it lets you store huge amounts of data, supports very good read-write bandwidth, as long as you're scanning data rather than doing lookups.
Okay.
And BigTable is more about modifying data and wanting to store lots of data and then adding more and more machines as you would need to, and it all just magically works. Right? Okay. So again, getting back to the building blocks, every single component that we build tries to reuse some component that we already built in the past, or in the cases when it doesn't work, then we go and rebuild that particular component. So for example, we needed to have a log service that actually worked reliably across lots of machines, so we built that. And MapReduction is just the computation on top of this, and clearly, because it's such a core piece of infrastructure, we certainly want to make sure that any new system that we build will work with MapReduction as well. And also, while at the same point, reusing as much of GFS and schedulers as possible, so we don't go in and implement every single part of the stack every single time a new application comes along. So the question is, are we done? So somebody asked us a little while back. We aren't even close to being done, because every few months, the scale just keeps increasing dramatically. And whatever we built before doesn't necessarily work yet. I mean, we do think about what is going to happen a year from now or 2 years from now, whatever, and we build systems to that scale. But unfortunately, what happens is the number of users keeps growing, which is nice, and the amount of data just keeps growing. So we have to go in and make sure that every single component that we have in the stack will have to be redone to scale to this extent. So every few months we have a new computational model that comes along, or we have a new bunch of tweaks that need to be made with our storage infrastructure, or with the way in which we do RPCs, or with the way in which we copy data across from one machine to a whole bunch of other machines. So all this is ongoing, and every so often, every 6 months, an engineer comes along with a bright idea that says that what if we do blah, and the blah will lead to either, say, a 100-fold reduction in latency for doing something, or will lead to a reduction in capital expenditure because we could use maybe 1/10 of as many machines as we did in the past. And you see the immediate sort of tangible benefits because it's scaling. It all scales, so you need to have very good background in algorithms to figure out that if you do X or Y, or if you introduce a new computational model, or if you change this part of the stack, then all these other things will be impacted along the way as well. So the goal really is what I said earlier. The goal is always to create something that's larger, that actually is higher performance, and make sure it works in more ways. So for example, one of the problems, so I'm just listing out a bunch of problems that are interesting open areas that we are always looking at. So replication and low latency access from across the world, that's a hard problem. How do you get a whole bunch of machines and a bunch of data centers across the world to reflect the latest version of what a user did? It's very hard. So we keep working on those kinds of problems. And then what happens if a bunch of data centers go down? Or what happens if a bunch of machines go down? There's a bunch of work that we have done so far to make sure that we cope with many of these things. But as the scale keeps changing, we keep solving more of these kinds of problems. Or even something like resource fairness. How do you have, let's say you have a lot of machines, how do you make sure that these machines, which are doing perhaps multiple tasks, how do they do resource sharing? How do you make sure that serving, which is, let's say that you're doing serving on search traffic, that's clearly more important than your latest map production is running on a few machines and copying data across. So how do you make sure that certain things are prioritized higher than others? That's an open set of issues we keep working on. Any questions before I switch to hardware? Yes?
I have one. So suppose you make changes to your MapReduce or any other algorithms. How do you go back and retroactively update the previous machine because you have thousands of them?
So the question is, if you go and change a fundamental library, like MapReduction or whatever, how do you go and change every other application that's running out there? So this gets into how Google engineering works a bit more than I had planned to, but the nice part is that we don't have too many legacy applications that we need to maintain over the next few years. So every time a person does a new build or picks up a bunch of changes, the improvements are reflected in their applications the next time they build it and push it out as well. As opposed to worrying about deployed software that is out in the field that we need to maintain for the next 5 years. So since everyone is building and pushing out binaries, they just pick up changes on a regular basis.
I'm sorry, I'm not sure I understood that.
Okay.
So you're saying you don't, you implement going forward, you don't maintain.
Right, so let me see. So the problem is that any software that is deployed out in the field, it's harder to change. That's why you have companies that have problems with legacy software. In our case, since we control all the applications, every so often, whenever the next version of a certain product is being pushed up, for example, let's say the video front end is pushing out a new version of their MapReduction, then they build and they pick up the latest set of changes and they push it out, which means that the average time that a binary is out in the thousands of machines is actually very, very low. So within the next a few weeks, it'll be fixed.
So it might be correct to say at any moment, any machine may have multiple versions, different versions of MapReduce library, for instance.
There's a lot of other things I haven't talked about that I can't even talk about at this point, which are things that we've done over time to make sure that versioning problems and data consistency, which is actually a whole bunch of very hard problems, are actually being addressed under the covers somewhere. So what happens if one server pushes, it actually talks a certain kind of protocol, and then you have another server that is the client? How does that actually respond to that? So there's a bunch of challenges in that area as well. Any other questions? Okay, so we've talked about a slew of products. We talked about some of the computing infrastructure that we have in terms of 3 pieces of technology. I mean, there are lots of others that we haven't talked about yet. But these are indicative of the kinds of problems that we like to solve. But beneath that, we have a lot of other things that are going on from a computing standpoint. So when we have a lot of machines, how do you build them to be cost efficient? How do you maintain them so that if you have multiple data centers, what if a bunch of these things die? What if how much power do you consume? All these are pretty interesting problems that we look at. Okay, so from a computing standpoint, there are lots of problems that are interesting. So there's issue around server design. So let's assume that we have this magical sort of systems stacks that work on a bunch of these machines. But how do you design the actual fundamental servers? What kind of motherboard do you choose? What kind of chips do you choose? How do you get the right kind of disks to work with the setup? And power efficiency is another area of importance. So I'll show a graph on this now in a slide. Networking is hard because you have lots of these machines, again, that need to talk to each other, and you want to make sure there aren't too many single points of failure, or there aren't, let's say you have a bunch of machines in a rack, you want to make sure that the switches have enough bandwidth capacity to send enough packets through so they are not the bottleneck, especially if they are talking about talking from one set of machines to another set of machines. So the classic philosophy we've had is we want to build a lot of these very low-end machines. So these are the PC servers. So pick up your favorite sort of motherboards that are commodity, pick up your favorite sort of RAM and disks, and build a lot of these things. And the assumption is that any company that sells ultra-reliable hardware, they don't necessarily work. I mean, the quality of of failures is perhaps lower, but you still need to compensate for the times when they fail by building a lot of these systems on top to recover when machines actually die or disks actually die. So the observation was, may as well just go for the cheap things and just build up a whole bunch of interesting software on top of it so that whenever they do die, because we know that they would die, that we would just sort of recover it in a nice, seamless way, and our products would just work. So a lot of you may have seen this picture. This was the initial Google machine. And you can see a bunch of Lego chassis over here which held all the hard drives. Things have evolved a little bit since then. This was a 99. And again, this gets back to the ultra cheap commodity hardware that we rely on, that we used to rely on. And in fact, these were a fire hazard too, because these were built out of cardboard. And no one told the people who were building these things, which is Larry and Sergey, that these things will catch fire. But they sort of optimized it by just having the cardboard with the motherboard on top, and then the disk just hanging over there. And then at some point when the Santa Clara Fire Department objected to this, they moved to a more traditional kind of data center model, which actually had, you can see some chassis over here, which encompassed the motherboard and the components. So yeah, and the company is a model of, and I'm just amazed every single time I see a data center just come alive. It's completely empty, and then a few days later it's all completely stacked up with machines, and it's all connected up, and all just magically works. It's kind of cool. So right now, it's again, the current design is slightly more professional. You can see there's like more cardboard over here. And again, it's still, a lot of these things are open because of power consumption and cooling issues. And again, it's the same sort of architecture. We have PC class motherboards, and we have very low-end IDE hard drives, and we run Linux on these things, and we build out all these software systems on top of these things that do not know where the machines are, why they're there, when they die, when they come back alive, and they seamlessly move things around. That's really how this all kind of works. So, taking a step back, what is Google doing in the hardware space as well as in the software system space? We've been working with chip manufacturers for a while because at some point we realized that the price per performance was actually getting better over time, over the last few generations. And the prices of these things was getting better over time as well. As in, you're getting cheaper components, and it was going the right direction. But the price per wattage, as in the amount of power that is being consumed on a performance basis, was actually kind of steady. And the problem is that if you want to cool a regular motherboard with a bunch of components, it may take like 250 watts to power it up. But then cooling also takes another 250 watts. And as these systems get more and more complicated, you had these huge cooling issues and power issues, and I think we did a graph that showed that if we just kept going at that rate, then the machines would not be the most significant component of our cost, but it would be power. So we've been working with chip manufacturers for a while to make sure that we have more power efficient chips as well as controllers that we can put into our data centers. And the data centers themselves are pretty interesting. So it was interesting as well in terms of how much cooling they require and how much time it takes to build up a whole bunch of these data centers and so on. So a lot of work in that area as well.
Do you use any colo facilities anymore, or do you do your own data centers?
So the question was, do we use colo facilities anywhere, or do we have our own data center? The answer is really a combination of both. I'm thinking of what I can say. So at some point we had it's a pity this is being recorded, but it's fine. At some point we had there were a whole bunch of data centers that were coming online because people thought there was a lot of money to be made in that. And over time, a lot of them went bankrupt because they couldn't find ways in which they could monetize other companies coming in and hosting these things. And then they started evolving into managed service providers and and other business models as well. So just to be safe, I think all companies, it makes sense to have a mix of colo facilities that you don't maintain as well as things that you own and maintain as well. I can't comment on exactly where we are in that spectrum. So doing a bunch of things in the hardware area and working with people who can supply us with things that will work well in our context. And also, as we talked about, we keep working on these larger and higher performance systems from a software standpoint, so that every few months we just change some part of the stack, and all the applications just benefit from that, and that's nice. So now that we have a lot of machines and lots of data and a lot of bandwidth that actually you have between different machines and different data centers, what do you do with it? And this is where we spend most of our time. We say, wow, we have all this data. What else can we pre-compute more? Can we make query processing faster by doing a bunch of these different things? Or can we offer a new feature or product that actually will be compelling to the end user? So it's really a mix of it's a full cycle. So we started products, and then the products work on top of a bunch of interesting system stack. And then you have the hardware platform beneath that. And as the products keep driving the improvements in the stack as well as the computing platform, we get more flexibility to go and do more and more cool things from the product standpoint. So that's what we keep worrying about. So behind every single service that we have a whole bunch of issues that keep coming up. And in hardware, networking, systems, algorithms, programming languages, statistics, product design, mechanical engineering. And so it's kind of a cool playing around, because with just having the right combination of hardware and software, we can solve more and more problems with that. And that's really what we try to do. So this is again a slide back to just to place in some context. And just in the last year and a half, just from this office right here, we've launched a whole slew of products in maps and in crawling, indexing, and so on. And every single one of these things uses every part of the stack we have, in terms of the standard machines, in terms of the storage that we have in GFS, or the analysis tool that we have from MapReduce, or the lookup kind of service that BigTable offers. And that's really what we try to do, keep building more and more of these things. Okay, any more questions? This is the upcoming talks in the next few weeks. Any other questions about building large systems at Google? Yes?
So I want to understand a bit about resource allocation. I understand that if you've got an app, you can say, hey, you can only use 500 machines. So at that level, you can constrain it. But do different apps use the same infrastructure, say GFS or BigTable, or do they tend to use their own copies? In other words, can you control the interference between apps? Not on a machine-to-machine level, but when they use some shared service, or don't they?
So the question is, are these different pieces of infrastructure, are they maintained by the different teams, or are they services?
And if they're services, are they services that multiple apps use, or does each app have its own copy of the service?
So do the different applications have their own copy, or do they have just one service that they can reuse? I mean the answer really depends on the actual service. Some of these are libraries, so every application can just reuse whatever functionality they get out of that. But things like storage, it again depends on a per group or per requirement basis. You might imagine that the ad system, which is pretty darn important to the company, or the search system, which is very important to the company, they would not be very open to having my favorite MapReduce running on their BigTable, right? And that's because it's scary that you could just bring down all of that. But then again, there are a bunch of things that are services. For example, there's one crawler. It doesn't make sense to have multiple crawlers. So you would have a bunch of machines that will just sit around and will crawl a bunch of the pages on the web, because that's an influence that we have over the rest of the web. So certain pieces of infrastructure make sense as services, and certain just make sense to have your own copy based on the kind of reliability or the interference you're concerned about.
But so you've avoided situations in which an unimportant app can bog down an important app by interfering in some shared service.
Right, so the question is, what about interference between one app and another app? That's another open area that we are excited by. And I can't tell you exactly how much progress we've made in that area, but it's an important area. The more we can reuse machines across different services, the better off we'll be. And it's a bunch of hard problems, so we solve it in ways that work for now, but may not necessarily work in 5 years. So, which is why we keep doing more of these things. Yeah.
So with more and more PCs these days coming out of Google software, how do you see this change, right, from centralized servers to personal desktops impact some of your current infrastructure, and what do you do to evolve?
So the question was, so far we have had a lot of backend services that we've controlled, and what happens if we start shipping software to a bunch of clients, and how do things evolve in that regard? A lot of the applications we've shipped so far have a very strong, they're pretty light on the end user's computer, and they interact a lot with the back-end technologies that we have. So they may issue a request back to us for storing some component, or may require some interaction that would be necessary on the user's computer. And so all the clients we've launched are light and thin on the user-facing side and have a lot of back-end interaction, which is where really our strengths are.
So you didn't really say much about how you manage software fault tolerance and redundant arrays of inexpensive computers and all that. There's a lot of existing software out there to do that sort of thing and manage clusters and so forth. Are you using some of the existing software, or doing something completely proprietary, or did you start with something that was out there and morph it into something proprietary, or what?
So the question was, how much do we reuse software that has been built up over time for reliability and scalability? Pretty much all the things that we do have been built up over time internally. So at some point we did have a few solutions that we tried out, and they just didn't scale enough. So in that situation, if it's open source, you could do a bunch of things with that. If it's not, then you may sort of reuse components. And you should realize that the benefit of having an existing stack is very important. So you don't have to redo the entire stack. So if you have an existing stack, you know that if you build some component on top of it, you could reuse, say, something like a GFS, or you could reuse some lock scheduler or a lock manager, right? And a lot of the existing software solutions out there don't necessarily have the same kind of benefit. And they haven't really worked with the number of machines or data centers or scale that we have. I mean, can you point to one large-scale system that works across many thousands of machines in a reliable, fault-tolerant way and processes so much of data? There's a lot of research in this area, but there's not any good commercially deployed solution that actually kind of works.
Do you have any internal systems to share the knowledge on this? It seems like each application that you build in a different office or whatnot could benefit the information that's learned in other offices. But how do you build special software to leverage that knowledge and transfer it across the different groups?
So the question was, how do we make sure that different offices share information about how to build different applications? So we have a lot of R&D centers at this point. We have maybe 20, 25, 16? 16. Okay, I thought it's like 20-ish. It's growing every single day. It's very hard to keep track of these things. So there's usually a bootstrapping problem. As in initially, when a team starts in a new operation, you have a bunch of learning that needs to happen. How do you use three of the things that I talked about? And there's a lot of internal knowledge about how that actually happens, but there's no substitute for having done a bunch of these things. So typically what happens is, in any of the R&D centers that we have, there are some people who move from, say, from Mountain View or from here or from New York or wherever to start setting up these places. So there is some initial knowledge to start the groups with. And then over time, you have enough expertise built up because you know what are the latest changes that are going on in BigTable, or what are the latest changes going on in systems that is relevant to you.
Yeah, I'm curious if a big table index can span data centers, and if so, like what are some of the big challenges there?
So the question is, does a BigTable itself span multiple data centers? I can't comment on exactly how it works across multiple data centers, but it's a very hard problem. And so that's one of the things that will keep changing as we keep growing inside. I mean, you can imagine how it works very well when you have small amounts of data. But if you start thinking about a petabyte of data thrown into a BigTable that has to work across multiple data centers and will have to be reliable up to the second in terms of coherency, that's really hard. Probably even impossible in some cases. So again, it gets back to the list of applications, and perhaps can get away with copying some data in a background process and can have master-slave relationships. These are hard problems, right? So the applications will pick and choose between the different options that they have, and will build up things that they need to build up into their infrastructure that keep changing as well. We can take 2 more questions, yes?
Can you talk a little bit about QA? What do you do to make sure code is scalable before it goes into production?
Okay, the question is about QA, and what do we do before, in terms of code going into production? Testing is a huge component, and engineers have a lot of unit tests, regression tests, and this gets into typical engineering hygiene and the usual things. And as you might imagine, every company that works in this space has a canary testing setup where they would push out a bunch of binaries and try it out and see if it actually works, if it has memory leaks, if it doesn't do the right things, and you have lots of monitoring built in. And once it actually kind of works, then you push it out to production. And there are glitches, and this is partly why it's interesting as well, because we are happier about making quick progress by doing a bunch of changes and pushing them out in production rather than waiting for a month to push out changes. Because as long as we can fix it quickly enough, we are in better shape. Actually, there used to be a badge of honor. People who brought down Google.com. And it's kind of nice to have that badge. One last question? Phil? Yes?
Yeah, I was just wondering about redundancy, like, do you have any measures or like any systems for actually, having a permanent storage for your data? Like, for example, if GFS, some of the GFS clusters go down or something, like, of course, they're like self-managing and they have a master system and stuff, but like, do you have a more permanent, like a state storage or something like that?
So the question is about tape storage versus disks. So one of the nice parts about GFS, as I said earlier, is that we haven't lost much data from it at all. Since the beginning of time, we've lost like 64 megabytes, or a chunk or whatever. That's not too bad. But as you might imagine, just for disaster recovery, every company has its own set of policies about what data do you want to maintain and what data do you want to keep around, and what is the cost of that. Again, that could be done on an application basis. But again, the goal that we have is always to build up the different components that will work across a large variety of applications, and then the applications, depending on how important they are, can pick and choose in terms of price, in terms of how expensive it is to maintain, and so on. All right, well, thank you for coming, and we'll be hanging out over here. And